Hello my friends, welcome back to my channel. This is the fourth lecture of the soil mechanics series. In this lecture I am going to talk about consistency of clays. Consistency of clays. Well, the term consistency, well, it indicates the relative ease with which a soil can be deformed. Relative ease with which a soil sample can be deformed. Well, this is a very important parameter and it is only associated with the fine grained soils, especially clays. Only associated with the fine grained soils, especially clays. Now, actually, what happens is that the physical properties of clays are considerably influenced by the amount of water present in them. That means, if we alter the water content of clay soil sample, then the consistency of the clay soil sample will change. And there are four stages or states of consistency that are used to describe the consistency of the clay soil sample. Well, the four stages or states that are used to describe the consistency of a clay soil sample are the four states that are used to describe the consistency of a clay soil sample. These are: number one is the liquid state, second one is the plastic state, third one is the semi solid state, and the fourth one is the solid state. These are the four states that are used to describe the consistency of a clay soil sample. If we alter the water content of a clay soil sample, then the states of the then the state of the clay soil sample will change from one state to another. Okay, so now there are some boundary water contents. There are some boundary water contents at which the clay soil sample undergoes a change from one state to another. Those are known as consistency limits. And the consistency limits were first demonstrated by a scientist known as Atterberg. So these consistency limits are also known as Atterberg's limit. Well, the Atterberg limit can be described very easily using a graph. This is the graph. Here it is volume, and in the x-axis there is water content. That is WC. These are the four states of consistency: liquid, plastic, semi-solid, and solid. Suppose you have a sample of clay, a sample of dry clay, and you increase its water content largely by adding a large amount of water, and you make a soil suspension. So we can say that the resulting soil suspension is in liquid state. That means suppose you have some amount of dry clay soil sample and you add some water into it and you form a resulting suspension, soil suspension, and it is in liquid state because it will offer no resistance to flow. In other words, we can say that the resulting soil suspension has no shear strength. Okay, so that means it is in liquid state. So now if you decrease the water content, like if you decrease the water content, beyond, if you decrease the water content beyond this limit, this WL, okay, then the state of the soil sample will change from liquid state to plastic state, and it will start offering some resistance to flow. That means it will start gaining shear strength. In this plastic state, the soil can be molded to different shapes without rupturing it due to plasticity. Now, if the water content is further reduced, and if the water content is reduced beyond this WP, then the state of the soil will change from plastic to semi-solid. In this semi-solid state, the soil will have no plasticity, and if the pressure is applied, the soil will simply crumple. Okay, this WL is known as liquid limit, and this WP, it is known as plastic limit. And what is WS? Well, up to this portion, up to this zone, the soil is fully saturated. That means all the void spaces are filled up with water, and there is also extra water. So now if you keep on decreasing the water content, like suppose if you reduce the volume of water, it will result in an almost equal reduction in the volume of soil mass up to this point. Okay, up to this point the soil is fully saturated up to WS. Now if you decrease the water content beyond this point, the saturation will start to drop from 100%. Okay, the soil, that means the soil will start become dry from this point, and there will be no change in volume because the water will lose from the void space, will start losing from the void space. Okay, so this one, this WS, this limit is known as shrinkage limit. If we decrease the water content beyond the shrinkage limit, there will be no change in volume, and the soil will start to dry up at the surface, and it will be no longer fully saturated. Now this liquid limit can be experimentally determined using Casagrande apparatus. Using Casagrande's apparatus. So actually what happens is that at a particular water content, a groove is cut in a pat of soil by a grooving tool of standard dimensions, and the groove will flow together for a distance of 13 millimeter under the impact of 25 blows in that apparatus. Okay. And plastic limit. This plastic limit can also be determined experimentally. So at a particular water content, the soil will just begin to crumble when rolled into a thread of 3 millimeter diameter. Okay. And shrinkage limit, well, beyond this water content there will be no change in volume. So that's all for today. We will meet in the next. Thank you.